Okay, so if we're going to do some testing, we need to have the ability to generate arbitrary queues so that Quick Check can actually test these things. So we need to do a new instance of arbitrary, which is a queue of A. So we can generate arbitrary queues, some type A. And the definition is that we need to define the arbitrary function, or the arbitrary generator. So how are we going to do that? Well, a queue of A's is built from two lists of A's. So we can generate two lists of A's. Then we can put them together to form an arbitrary queue. So let's do that. Let's do the following. Let's take the front to be an arbitrary list, and the back to be another arbitrary list, and then we return the queue that we formed from the front and the back. So there's a first attempt. Let's try and compile that. That didn't go so well. So what does the error message say? No instance for arbitrary A arising from A use of arbitrary. Possible fix, add arbitrary A to the context of the instance declaration, blah, blah, blah. So what we're trying to do here is generate the arbitrary front of the list and arbitrary back of the list. This is a list of A's and this is a list of A's. But you can't generate an arbitrary list of any type A. It has to be a type A which you know how to generate. Right? So we're trying to generate a list of A's here and a list of A's here. We can only do that if A itself is in the arbitrary class. So actually you can have an instance declaration that has a type constraint, a class constraint, and that is that if A is in the arbitrary class, then we get an arbitrary at this type. So we need a constraint, which is this thing here, and this says if A is in the arbitrary class, then we are putting QA in the arbitrary class as well by defining this function. So let's try that. That should hopefully, so we can sample arbitrary at type Q of, let's say, int. So it's not a queue of int, it's a generator for queues of int. We're sampling that one there, and there we see a bunch of samples because they're printed out because we've derived show for this thing. Okay, so having done that, we can do some testing. And in the process of testing, we will see that we haven't quite finished our definition. So let's try some quick checking of, let's say, remove. Okay, that failed pretty quickly. We try to test removing in the case when both lists were empty, and then that will fail. So we have some operations that will fail, and that's what they're intended to do. So what we've done wrong is not implement them incorrectly, but we've actually specified the property incorrectly. This only holds if Q is not empty. So we can represent that using the quick check operator to filter. So we can say not is empty Q. For all queues which are not empty, this property holds. So this is an invariant that should always hold for the arguments to this function, and we can represent those. So now they're kind of documented, and that's not only true of remove, but also of the add. So let's have a look at what happens now when we try that one again. Oh, we still have a problem. We have a non-empty queue. There it is, which still causes us to fail. So what's going on here? Well, what we've got is we've got the front of the queue is empty, but the back is not empty. Now, that's not a good case. We don't really want to end up with the front becoming empty when the back is not empty. What we need to do is move the guys at the back of the queue to the front of the queue to make sure that that never happens. So in fact, that's a general invariant of the data type. That is a property that should always hold of the data type, namely that if we have a queue then the front of the queue should never be empty if the back of the queue is empty. So how are we going to express that? Well, one way to do it is to say that it's never the case that the following holds: that the front is null and the back is not null. So that should never hold. So it should never be the case that the front of the list is empty and the back is not empty. So that's a property that we expect to hold, we want to hold for all queues. But we're not going to get it for free. We're going to have to make sure that that always holds. But if we're going to test it, we better make sure that we never generate queues that have this property. So what we need to do is to make sure that we build queues so that if the front is null, then the back is also null. So we can do that here. We can sort of generate random arbitrary front and back. But what we can do is say if the front is null, then we'll build the queue back front. Otherwise, we can build the free queue front back. So we've got a candidate front and a candidate back, but we might actually swap them round if this one turns out to be empty. Okay, so let's reload that. Let's test the invariant. So the prop invariant now will test our generator. It tests that we never generate anything which is bad, and that is indeed the case. So the generator is good. We never inviolate the generator. So now let's go back and test some of the earlier cases. Let's try the property remove, and we see that works very well. Everything seems to be okay because we've generated. Let's try some of the others. Let's try quick check prop add. That's also great. But what are we actually checking with that? Well, we're checking that the implementation we have here agrees with the original implementation. But what we haven't checked, what prop add does is it creates a new queue. So any operation which creates a new queue, we need to make sure that it satisfies the general invariant property that we expect for queues. And that's this one here. So what we should also test, so a lot of tests going on here, is another invariant. So let's separate these testing of the comparison between the two structures and the invariant. But the property of the add, the invariant for add, let's call it prop add inv. If we have an element A and a Q, then adding A to Q should satisfy the invariant. So when we add A to the Q, then the result should satisfy the invariant that we have above. And then the same goes for testing not only add, but all the other operators, for example, the empty case. The property invariant for empty. And also the remove function. The property remove function should be such that if we remove something from the queue, then the result should satisfy the invariant. But of course, you have to remember that this guy will only work if the queue is non-empty. So we better add that constraint, that filter to our quick check property. So it only works if the queue is non-empty, of course. We don't expect it to do anything sensible for an empty queue. Let's put those all, format those all. So there are our three invariants. Let's try one of them out. Let's reload that. Oops, I've got a multiple declaration. Oh, it's the invariant that I'm defining. Okay, so let's quick check one of those. Let's have a look. What did we do before? Prop add. Let's add the invariant. Whenever we add something, do we satisfy the invariant? And we don't. When we add something to the invariant, you see actually we're testing at the very simple type of blobs, but actually it doesn't matter because it still catches the error. What happens when we add something to the empty queue? Well, we add this to the back of the queue, but as soon as we do that, we fail to satisfy the invariant. The invariant fails. Let's try the other one as well. Let's try remove. We also have that. If we remove something from this queue, what we do is we take out this element from the front, and we end up with a queue which does not satisfy the invariant. So we need to fix our definitions to make sure that the invariant is always satisfied. So where does the invariant go wrong? It can go wrong in both remove and add. And it goes wrong precisely when the front ends up being empty. So we're going to fix this in a simple way by saying, well, what we've done here is we've used this kind of rather stupid constructor, the constructor that just blindly puts these two things together. And the constructor shouldn't just blindly put them together, it should make sure that the invariant is satisfied. So the way it can satisfy the invariant is to make sure that whenever the front is empty, we move the back of the queue to the front. So what we're going to use is a smart constructor called fixQ, a little function. And let's define it down here. So fixing a queue, if we have an empty front of the queue and the back of the queue, we need to fix it. Fixing a queue with a front and a back where the front is not empty, we don't have to do anything. We simply build the queue from the front and the back. But in the case that the front is empty, we'll take the whole of the back of the queue and we'll shuffle them over into the front of the queue. That is to say, we're going to build a queue by reversing the back of the queue and putting them in the front. And now we have an empty back of the queue. So the waiting room at the front is now empty. So we shuffle everybody who was at the back of the queue into the front, leaving the new back empty. So this will guarantee that we will satisfy the invariant. So if we reload now and we try those, then we'll see what we should pass those. And indeed we do. So we did so by replacing the stupid constructor by a smart constructor, one that applies a little bit of intelligence before building the resulting queue. Now, one thing you might notice here is that the whole point of this representation was to be quicker than the other, more efficient than the other version. And now we're using a recursive function. But we only use this recursive function when the front becomes empty. And any element in the back only gets shuffled to the front once in its lifetime. And so every element is responsible, the reverse is responsible for one extra computation step for every element that ends up being removed from the list. And that's a small constant overhead for each element. So it's not a big cost that we had potentially in the slow version. So this cost here averages out, it amortizes over the cost of manipulating all of the elements of the list.